All right, so our quick look at the calendar. Happy Friday. Today we are talking about something called the second derivative. Again, trucks is due today. Arbitration was due last class. I accept things late, but the sooner you turn them in, the better. So hopefully lots of projects in those folders for me. Monday coming up is our review day. So we have no agenda on Monday, although I will give you another activity that you'll work through that will hopefully help solidify some of these concepts. And then Wednesday coming up, there are no day classes. It's a professional day. So we will not meet Wednesday coming up, but our test will be Friday, okay? So review day Monday, test on Friday, 1 week from today. Questions on the calendar? Okay, so let's start here on page 64. And one last thing before we jump in at the top of page 64. We haven't talked together about the weight of all the different things that I'm grading from you guys, right? There's homework, there's questions of the day, attendance, we got a quiz, 2 projects, and then the test coming up. So if you read the syllabus carefully, then you've already seen this, but I will tell you now, if you haven't looked at it, that you guys are going to tell me how you want me to grade you, and you don't need to each give the same answer. It's not a class-wide decision, it's an individual decision. So I've given a few kind of standard ways that you might choose to be graded. One of them is just called standard, and you can see the different weights there. Another one is test heavy, which I have written here. It's a bad choice for most, but occasionally there's somebody who feels like they can get away without doing any of the homework and without doing any of the questions of the day, and maybe not even attending regularly and still do well. So they're putting all their eggs in the test basket, and I don't want to stop you from doing that, but I think it's a bad choice generally. A lot of folks end up going test light, where they push as much away from the tests as possible, so bumping up the attendance, questions of the day, the homework, projects, all that stuff. So here are 3 options, but actually you have more options than that. You can kind of mix and match, as long as you pick numbers that are in the ranges that I've prescribed here and add up to 100, okay? You are going to make that choice the class after I hand you back your graded test. So you don't need to make the choice now. You're going to take the test on Friday. I'll give it to you the following Monday. And then the Wednesday after that, after you've already seen your project grades, your quiz grade, your test grade, and you've gotten a sense of like how regularly you can commit to doing this homework and the questions of the day, that's when you're going to make your choice, okay? Any questions on that? Okay. All right, so at the top of page 64, daily summary. Can we go to Cameron? Thank you. So number 1A, it says for y equals x cubed minus x, we're going to find y of 2, y prime of 2, and then these other things here that we haven't seen before. But let's go ahead and start off by finding y of 2. So that's kind of a funny way, but presumably you know I mean f of 2, right? It's just the function evaluated at 2. So 2 cubed minus 2, no calculators on any of this. 6. Okay, fair enough. Let's go ahead and find y prime. So do your quick calculation for the derivative. So I bet everybody got the 3x squared, but I'm wondering if some people missed the derivative of minus x. What is the derivative of minus x? It's minus 1. It's an invisible minus 1 sitting in front of that x. So it's 3x squared minus 1, which means that we can find y prime of 2 by just plugging 2 in for that x. Again, no calculators. Is that 11? Okay, now it says y double prime, symbols that we have not seen before, but it just means take the derivative of the derivative, right? This 3x squared minus 1 is a perfectly good function that can be differentiated. You can take a derivative of it. So the notation, not surprisingly, is y with 2 apostrophes up there. That's going to stand for second derivative. So what's the derivative of 3x squared? 6x. What's the derivative of minus 1? 0. So the second derivative here is 6x. And so we can take that and go ahead and calculate y double prime of 2. by just plugging 2 in for the x. Easy peasy. Okay, but that was so much fun we could just keep going. So y triple prime is the third derivative, or the derivative of the derivative of the derivative. What's the derivative of 6x? 6. And so y triple prime of 2 is 6. It's always 6 for any number you plug into the third derivative here. Okay, I'm going to do a calculator thing really quick. I know that we don't all have the same calculators, so I don't want to spend very much time on this piece. But if I ask the calculator for n deriv, which on my calculator is inside of math, and it's just off screen, I think it's number 8. That's how I find it on this calculator. If it's not there for you, I'll help you later on. N deriv, then you type in the function, which was this x cubed minus x. And then the syntax says you put a comma and then the variable. The variable for us is almost always x, but you still have to put it. And then finally one more comma, and then what I said here is a 2. Why? What is that 2 representing? Nope, that doesn't represent the second derivative. It represents the x that you're plugging in. So we're finding y prime of 2 here. So the calculator should give me 11 if I've done this right and it knows what it's talking about. It didn't give me 11. It's not 11. Well, the answer is 11, but the calculator doesn't know any calculus. The calculator is approximating the answer by doing some secant lines that are really, really close to being the tangent line, but it's not perfect. So anyway, your calculator can find numerical derivatives pretty accurately, not 100%. So that's how you do it on the calculator. Like I said, I'm happy to walk around during the activity and make sure everybody can do it on their calculator. So hold your questions on that if you can't quite do it on your calculator just yet. And then we'll show you real quick how to do this on GeoGebra. Make this bigger. Okay, so the first thing was f of x equals x cubed minus x, yes? Okay, and so there it is. And then if I just type in f prime of x, it gives me the answer, 3x squared minus 1. See it? It graphed it for me too. So 3x squared minus 1 is something that your TI-83 cannot tell you. It didn't tell me 3x squared minus 1. It doesn't know how to do that. It can plug a number into that thing, but it can't actually find that thing. So if I wanted to find f prime of 2, which was 11, I just type in f apostrophe 2, and it tells me, okay, it's 11. And I think that this guy can go farther. F double prime of x, what was the answer? 6x, right? All right, so I'm going to hit enter. 6x, there it is. F1, 2, 3 of x, what's the answer there? 6. So it's really easy to find derivatives on GeoGebra. It's also kind of nice that if you type in a more complicated function like 3x to the second minus 4x plus 2, and then remember we talked about what was the rule we'd have to do in this case? That's a product rule, right? All right, there. I mean, it did it. I'll go back. So maybe I don't want to go back that far. I don't want to retype it. But it did it, and it didn't take very long. There's, oh, that's just g of x. I didn't do g prime yet. So let's see how long it takes to do this derivative. Ready? 3, 2, 1. There it is. And doesn't it look like the product rule? Right? First times derivative of the second plus second times the derivative of the first. I'm not looking, it might not be exactly that order in the terms, but it knows the product rule and many other rules that we don't know yet ourselves. Right? So it's kind of nice. Certainly much better than this guy. Okay, turns out you can get your calculator to graph derivatives. You can try that later. We're not going to do it now. And we're going to move on to number 2, which has to do with notation. It says those primes can get unwieldy. So if you want the fourth derivative, at some point we probably stop writing prime, 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 prime. You just put a 4, but you got to put it in parentheses. The parentheses is the mathematical way to say this is the number of derivatives that I want. It's not a power. If you put that 4 up there without parentheses, I'm going to think it's a power. I'm going to think you mean, oh, f of x times f of x times f of x times f of x. Parentheses mean derivative. Then we had Leibniz's notation here. So this kind of looks funny. We remember we saw dy dx was just the first derivative, right? And so if I want the second derivative, I mean, it makes sense that there are some 2's that are going to happen here, but the places that they happen, it's kind of funny. There's a 2 that goes up there and a 2 that goes here. Like, they don't quite go in the same spot. I can explain why, but unless you're interested, I'm not going to take class time with it. So if you want to know why they don't go in the same spot, just see me after class. And so now the other new thing for today is concavity. So let's see, what can we say here? This very first function right here, if I just think about some tangent lines, so like steep downhill, not quite as steep, flat, not too steep uphill, and then really steep uphill. If I'm just thinking about the slopes of these lines, just a list of numbers, something like maybe that's a -2 and a -1 and a 0 and a 1 and a 2. Yeah? Just making up numbers. What can you say about that list of numbers? It is getting larger, right? So that's increasing. And anytime the list of slopes is increasing, we call the function concave something. It's either up or down. In this case, it's concave up. So we call this guy right here concave up, which just means that the derivative is increasing. But it turns out there's kind of an easy way to think about this without drawing all the tangent lines. It's down here. Levi, can you read the note? Thank you. Yeah, you got it? C up, concave up. So if it looks like a cup, if it can hold water, it's concave up. This next guy, the water would fall right out. If you put water inside of here or out here, it would just all fall down, right? But if you put water in here, it stays in there. So the one that looks like a cup, we say is concave up. So I guess this guy had better be concave down. If you draw the tangent lines and just think about the slopes, instead of being a list of increasing numbers, it's a list of decreasing numbers. Levi, you had such enthusiasm for the first one. Can you read the next one too? Got it? Round. A couple of eyes, maybe a nose. So if it looks like a frown, it's concave down. Most graphs are actually some combination of the two. So for example, this first part of the last graph from here to here, if I continued that trend, would it be like a cup or a frown? It would be a frown, right? Like if I just kind of continued what it looks like it's doing, then it would be a frown. So that part on the x-axis, this guy's concave down until we get to the origin. And then it changes its mind. Because out here, it looks like something very different. And if I were to continue this green thing, what would it look like? A cup. And so that part on the green is concave up. So way out here is concave up. Okay? So most graphs change their mind, sometimes several times. All right, and then finally on the next page, a couple of fill in the blanks. Let's go to Tyler for 4. Okay, let's fill in the blank. If your derivative, this is not a question from today, this is a review. But if your derivative is positive, then what can you say about the original graph? Increasing. Keep going, Tyler. So this one's decreasing. If your derivative is negative, then your function is decreasing. Now we'll go to Kevin for the new thing. Okay, I'm just going to ask you to read that symbol one more time. Greater than 0, yes. So if f double prime is positive, see if we can figure out which case we're in. I want the second derivative to be positive. Okay, which means that, okay, so f double prime, I'm just going to rewrite it like this. Just f prime prime, throwing some parentheses in there. So forget about what function is in the parentheses. But some function in there, which I'm going to temporarily cover up, has a derivative which is positive, yes? That's what this is saying. So if the derivative of what's in there is positive, then what is the original function doing, Dan? Oh, undo. So it's increasing, right? This is what we saw on the top of the next page. If a function has a derivative that's positive, then the function is increasing, which means that this thing I'm covering up is increasing. The derivative is increasing. Which picture was that? First or second? Where the derivative was increasing. It was the first, right? It was this list of numbers that was increasing. So it turns out that second derivative positive goes hand in hand with concave up. Graph of f is concave up. And then on the other side, if f double prime is negative, then the graph is concave down. So that last sentence is real important for us today. Second derivative positive, concave up. Second derivative negative, concave down. Which means, I guess, that it's natural to take a look at number 5. That if the concavity is going to change someplace, then what kind of a number might we have? The concavity changes. Yeah, it's going to be critical for a certain function, absolutely. But here we've got the concavity changing. Either the second derivative is 0, not positive or negative, right? It's the number in the middle where things kind of change. So if you're looking for places where the concavity is going to change, second derivative is 0 or maybe undefined, just like critical points, but those were for first derivative. Places where the concavity changes is like a critical point, but for the second derivative. Okay. Yeah, a place where the concavity changes would probably be max or min of the first derivative. That's right. Okay, so group activity starts there. Give it a shot.